graphs of functions related to exponential functions. So in the previous lesson I described to you what the function y equals a to the x to the power of x, what its graph looks like. We discussed the impact of parameter a on the graph. We learned that if a is greater than 1, the graph is strictly increasing, and also if a is between 0 and 1, the graph is then strictly decreasing. Now we will build on this knowledge and try to extend it a little bit. And what I'm going to do today actually is I'm going to investigate two different families of functions related to this function. So the first family of functions that is related to this are the functions in the form y equals k times a to the power of x. So I would say that they are k multiples or k times greater functions than this function. The number k here is a real number which is different from 0, because if it was 0 it would be just not interesting. The function here would be a 0 and it would be a constant 0, so nothing interesting there. So these are the conditions that we suppose are true for the coefficients. For the base a, it has to be positive and not equal to 1, and for the coefficient k in front of the a to the power of x, we suppose it's different from 0. And now the question arises here: what is the impact of the change in the value of k on the graph of the function? So let us investigate this, and the best way to do it, as you already know, is to use GeoGebra, because it allows you to do your research very quickly. So here what I have is a model of a function of the exponential function, and the exponential function here is in the form f of x equals k times a to the power of x minus m plus n, but my values for m and n, as you can see here, m is 0 and n is 0. So if you imagine that m is 0 and n is 0, what you get here is the function f of x equals k times a to the power of x. So here what the value of a is, you can see a is 2. So the red function in the picture is the function f of x equals 1 times 2 to the power of x. So this is the function with the coefficient k equal to 1. And if you imagine that you just remove it, because you do not have to write multiplication by 1 explicitly there, so this function is the original function a to the power of x, where a is 2. Now we can observe what happens if we take this slider and move it a little bit. So if we change the value of the coefficient of k. So let me do it. What I do now is I'm going to increase the value of k to greater values. So now it's 1, and now let me increase it. So you see what happens. The function seems to be scaled in the vertical direction. All the points of the function move upwards. If I decrease k, all the points of the function move downwards. Now, if I want to compare this function with its original form, the f of x equals a to the power of x, I can make it visible there on the graph. So this gray curve here is the function y equals 2 to the power of x, while the red one is y equals k times 2 to the power of x. So now, for example, k is 2. So what happens? You can observe this together with me. So this point here on the gray function was the point with coordinates 0 and 1. Now this point has moved upwards to the vertical coordinate 0 to the vertical coordinates 2, so it's twice as distant from the x-axis as it was on the gray function. So this point moves twice as further. Well, its distance from the x-axis is twice as large as the distance of the original point. This point here was the point with coordinates 1 and 2. So this is the very important point on any exponential function. And now this point has moved to this new position with the vertical coordinate of 4, which you can see is twice as large as its old vertical coordinate, which was just 2. So what happens? Well, the entire graph of the original function is scaled in the vertical direction by the scale factor of 2. You can see it. If k was greater, say 3 or something, it would be scaled by the vertical factor of it would be scaled vertically by a factor of 3, and so on. Now, let me get back to the original value of k equal 1. Now, what happens if I decrease the value of k from the number of 1? So let me take k equal to, say, 0.4. You can see it yourself. It's now 0.4. So what happened is that this point, 0, 1, on the original gray curve, moved to a new position here, which is 0 and 0.4. So it's at 40% of the distance from the x-axis as it was originally. Original distance was 1, now it's 0.4. This other point here, with original coordinates 1 and 2, has moved to the position with the vertical coordinate 0.8, which is again 40% or 0.4 times as much as it was before. So what happened now is that the graph of the function k times x to the power of 2, k times 2 to the power of x, or k times a to the power of x, this graph is scaled vertically by the scale factor of 0.4. So I would say it's shrunk toward the x-axis. Okay, so it's shrunk. Before, when k was greater than 1, it was stretched away from the x-axis, and when k is less than 1, it's shrunk toward the x-axis by the scale factor k. Now, what happens if k is 0? Well, if k is 0, it's not interesting. As I said, the function would be 0. But let us imagine that k is just -1, like this. If k is -1, what happens here is that you can see that this new graph, -1 times 2 to the power of x, is a reflection of the original graph in the x-axis. So the graph becomes reflected. This point here with coordinates 0 and 1 has the new coordinates of 0 and -1. So what happened? The vertical coordinate of the original point was multiplied by -1, and it becomes -1. This point had the vertical coordinate of 2, and when you multiply it by -1, you get the vertical coordinate of -2. So what happens when k is -1? The graph is reflected in the x-axis. But, okay, let us take the value of -2. If I take the value of -2, you see what happened. The graph is not only reflected in the x-axis, but it is also stretched away from the x-axis, so it's scaled by the vertical scale factor of 2. The distance of this point is twice as large as the distance of this point from the x-axis. So the distance of this point from the x-axis was 1, and the distance of this point from the x-axis is 2. So it's scaled vertically by a scale factor of the modulus of -2, which is 2. So it's twice as distant, and each point of this function is twice as distant from the x-axis as the corresponding point on the original function. Okay, so when k is negative, well, it means that the original function has first to be reflected in the x-axis and then scaled vertically by the scale factor modulus of k. The scale factor has to be positive, so therefore I use the modulus there. Now imagine that k is -0.4, again, like this. So again, you see there is a correspondence with the case of k being 0.4, but this time it's not only shrunk, but it's also reflected in the x-axis, as can be seen here. Okay, so let me get back to my presentation and let me answer this question with some theorem or something. So the question was, what is the impact of the change in the value of k on the graph of the function? So the original function was a to the power of x, and the new one is k times a to the power of x. So I have a theorem called relationship between the function f, y equals k times a to the power of x, and the function f sub 0, y equals a to the power of x. It may remind you of some corresponding theorems that you encountered when we talked about power functions or rational functions and so on. So this should ring the bell at least. And now we will do the same thing again, but for a different function. So let us read this. Depending on the value of k, the graph of the function f, y equals k times a to the power of x, is obtained from the graph of the function f sub 0, y equals a to the power of x in the following way. If k is positive, the graph of f sub 0 is scaled vertically by the scale factor k. You saw that in the model in GeoGebra. If k is negative, the graph of f sub 0 is first reflected in the x-axis and then scaled vertically by the scale factor of modulus of k. As I said before, the scale factor has to be positive, and therefore when k is negative you have to use the modulus of k here to get the positive scale factor. Now, the effect of the vertical scaling depends on the modulus of k. If modulus of k is greater than 1, it means that k is either greater than 1 or less than negative 1. In both situations, the modulus of k is greater than 1. Then all the points of the graph of f sub 0 move further away from the x-axis, and the graph is stretched away from the x-axis. So it is stretched away from the x-axis as it's written here. On the other hand, if the modulus of k is somewhere between 0 and 1, for example, it would mean that k itself is either greater than 0 and less than 1, or less than 0 and greater than negative 1, then all the points of the graph of f sub 0 move closer to the x-axis, and the graph is shrunk toward the x-axis. So you see, either you stretch it or you shrink it. It depends on the modulus of k. This graph shows you all the situations, and you can study it later in more detail. It shows you all the situations for the functions y equals k times a to the power of x. So what can happen? Either a is greater than 1 or a is between 0 and 1. What can happen? K is either positive or k is negative. And here are the effects you observed on the graph yourself. So if k is positive, you can see yourself that the function has the domain of all real numbers. The range is the numbers, all positive numbers, so the numbers y which are greater than 0. It's strictly increasing, bounded from below by 0, not bounded from above. It's 1 to 1, as is documented or indicated by the fact that it passes the horizontal line test. Has not got a strict maximum nor minimum. As x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches 0 from above, like this. When you take positive k and a between 0 and 1, you get this. So there is the only difference that it's strictly decreasing when you compare with this one, and the difference is in the asymptotic behavior. So as x approaches or tends to positive infinity, y approaches 0 from above, you can see it yourself, and as x approaches negative infinity, y approaches positive infinity. Now let us look at this case of negative k and a which is greater than 1. So this function is the reflection of this one in the x-axis, so it is reflected. So therefore well, the range is the set of all negative numbers. It's strictly decreasing this time. It's bounded from above by 0, not bounded from below, 1 to 1 again, and doesn't have any strict maximum minimum. It's the same for all these situations. And the asymptotic behavior is as follows: as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches 0, but from below. You can see it yourself. This case here is the case of negative k and the base between 0 and 1. So again, it should be the reflection of this curve here in x-axis. So you can see it here like this. So the domain is the set of all real numbers, the range is the set of all negative numbers. Now it's bounded from above by 0 and it's not bounded from below. It's strictly increasing this time. It's 1 to 1 again. And as x approaches infinity, y approaches 0 from below, and as x approaches negative infinity, y approaches negative infinity. These are the facts that we learned from the model, and now let us move to the second family of functions that we are going to investigate today, and it's the family of functions f in the form y equals k times a to the power of x minus m plus n, where here are the conditions for these parameters. A is the base with usual conditions. It has to be positive and different from 1. K, as before, is the scale factor. It's the number, it's a coefficient in front, which has to be real and different from 0. And m and n are two constants which are real numbers here. They can be positive and negative, both of all. And also they can be zeros. Okay. Now, the obvious questions here. What is the impact of the change in the value of m on the graph of the function, and what is the impact of the change in the value of n on the graph of the function? So let us investigate this thing here on the graph. So here again we are in GeoGebra. Let me choose k equal 2. Okay. Now let me hide this function a to the power of x. Let me choose a as 2, so we have the function 2 times 2 to the power of x, as you can see yourself. And now let me change the parameter m. If I increase m, what you see, the entire graph is translated to the right, and it's translated by the distance equal to this parameter m. So for instance, this point had the original position here. If you want to see the original curve, we can do that. I will just make this visible. Here is the original curve. You see it here in this shade of red. And this point 3, 2 had the original position here. So let me move the parameter m back to its original position. So the original value of m was 0. So you see from 0, when we increase m, this point moves to the right, and when m is 3, it has moved by 3 units to the right. So it is a translation. It was translated by 3 units towards the positive direction of the x-axis. The same goes for this point here, whose original position was 1, 4, now it's 4, 4. So its x-coordinate has changed, it has increased by 3. When m is 2, the translation is just 2 units to the right. You can see 2 units to the right. This is the original position of this point, and now it has moved by 2 units. This was the original position of this point, and it has moved by 2 units, as you can see. So what happens when m is negative? Of course, when m is negative, we translate the graph, but this time in the negative direction, to the left. So for instance, if m is negative 2, like you can see here, the point minus 2, 2 has been moved from its original position here by 2 units to the left. and this point has been also moved by 2 units from this original position here. So m has the effect on the horizontal translation of the graph, on the horizontal position of the graph. If m is 0, this is the original function k times a to the power of x, and when m is increased, we move to the right. When m is decreased, we move to the left. So this is it. Now let me get m to the original value of 0, and now let me investigate the effect of n. N is this value here, which you have to add to the function. So when you increase n, what happens? You see, when I increase n, the whole graph moves upwards. So now the n is 1. So everything has moved upward by 1 unit. So this point here had its original position at 0, 2, and now it is at 0, 3. This point had its original position here at 1, 4. This is the 1 and 4 coordinates, and now it has the coordinates of 1 and 5. So everything is translated upwards by 1 unit if n is 1. If n is 2, everything is translated by 2 units upwards. If n is 3, everything is translated by 3 units, and so on and so on. So increasing n moves the whole function upwards. When I decrease n, the whole function moves downwards. When n is negative, well, the function is moved downwards from its original position. So this point here had its original position here at 0, 2, now it's 0, 1. So the vertical coordinate has been decreased by 1. This point had its original position here, it was 1, 4, now it's just 1, 3. So the vertical coordinate is 1 less. Okay, so you see the effect of n. Now if you set both coordinates, both values of m and n different from 0, see what happens. These two effects combine. So first let me shift the function in horizontal direction by 2 units. So I take m equal 2, and in the vertical direction by 1 unit. So I now take n equal 1, and what I end up with is this new position. So there is a shift in 2 units to the through 2 units to the right and through 1 unit upwards. You can see that there are these dotted lines, whatever, and these lines are also they have their corresponding original positions in y and x axis. So these lines coincided, this vertical one with the y-axis and the horizontal one with the x-axis, when m and n were zeros, but now they are shifted together with the function. So yes, so you can now see that the original position of this point with coordinates 2 and 3, well, it had to be this, and perhaps no, it had to be perhaps here. Yes, no, here, it was here. So from this position it's shifted by 2 units to the right and 1 unit upwards. So m is 2 units to the right, n is 1 unit upwards. So this point is shifted here, and this point had its original position here on this original graph, and it's been shifted by 2 units to the right and 1 unit upwards as well. Okay, so now as for the asymptotes, there is just one horizontal asymptote, and when you shift the function, the original function, like that, you see that also its horizontal asymptote is shifted, and it becomes y equals 1 in this case. Okay, so let me get back to the presentation and let us look at some answers. Okay, now let us look at these results. I have a neat theorem here for you to see what happens, what the relationship of the function f y equals k times a to the power of x minus m plus n and the function f sub 0 y equals k times a to the power of x, what this relationship is. So the graph of the function f is obtained from the graph of the function f sub 0 by translating it horizontally through m units and subsequently vertically through n units. If m is greater than 1, it moves to the right. If m is less than 1, it moves to the left. If n is greater than 1, it moves upwards. And if n is less than 1, Again, if m is greater than 0, it moves to the right. If m is less than 0, it moves to the left. If n is greater than 0, it moves upwards. And if n is less than 0, it moves downwards. This is documented by this figure here. So the original function is in gray color, and the translated one, the general function, the function f, is here in red color. Together with the function, also the vertical and horizontal axis is translated in these two lines. The line y equals n becomes the horizontal asymptote of the function. There is the correspondence between some points, so this point on the gray function corresponds to this point on the red one. So it's shifted by m units in the positive direction, horizontal direction, and by n units in the vertical positive direction. And this point corresponds to this one, and the translation is actually the same. So this is it. We will now try to use it shortly in exercises.